The F-35 Lightning II is redefining the battle space. Its advanced sensor fusion provides an unparalleled view of the skies.
Imagine a fighter jet that does not just fly into battle, but quietly rewrites the rules of modern war.
Stealth, sensor fusion, and short takeoff and vertical landing capability combine in a single machine that has become the core of many air forces.
In this video, we will break down the structure, the engineering, and the hidden systems that make the F-35 so advanced.
From its stealth-shaped airframe to its powerful engine, to the lift system that allows vertical landings. We begin with the airframe, the skeleton and skin that must survive high loads, carry fuel and weapons. The F-35 uses large composite sections, smooth seams, and carefully aligned edges to scatter and absorb enemy radar energy. Every curve and every angle is the result of thousands of hours of computational fluid dynamics and radar cross-section modeling. Notice the smooth, diverterless supersonic intakes. They remove complicated splitter plates and reduce the number of radar-reflecting edges.
When the internal weapon bays are closed, the aircraft preserves its stealth profile and can approach heavily defended airspace.
But to understand why this fighter is so different, we need to zoom inside the materials, the engine, and the lift system.
The outer shell of the F-35 blends metal and advanced carbon fiber composites, coated with radar-absorbing materials.
Fasteners are flush, panel gaps are tiny, and exposed edges are oriented in a way that redirects radar energy away from its source.
Unlike older fighters with many right angles and external pods, the F-35 integrates sensors into the body to keep its shape clean.
The canopy uses special coatings to shield the cockpit reflections and hide the pilot's helmet from hostile radar systems.
Below the cockpit, the fuselage curves into the twin internal weapons bays, which allow the jet to carry bombs and missiles without external drag. These diverterless intakes use a raised bump to push the turbulent boundary layer away, feeding only clean supersonic air to the engine.
Every diagonal line on the lower fuselage is carefully chosen to return radar energy away from the threat's receiver.
Inside the skin, a sturdy central spine and multiple bulkheads carry the loads of high-speed turns, while also holding large fuel tanks.
In its pure stealth configuration, no external weapons or fuel tanks disturb the smooth wing and fuselage junction. Even the landing gear doors sit flush and follow stealth-friendly angles to avoid becoming bright spots on radar screens.
As it turns, you can see how the jet looks like a single, solid shape, not a collection of separate pods and protrusions.
When stealth is not needed, additional pylons can be fitted here, but the clean configuration is the one designed for penetrating defended airspace.
The outer shape must satisfy both aerodynamics and stealth, balancing lift, drag, stability, and low observability.
Now that we have seen the outer design, it is time to look at the heart of the aircraft, its engine, and its lift system.
The F-35 is powered by a single Pratt Whitney F135 turbofan, one of the most powerful fighter engines ever built.
Its nozzle uses sawtooth edges and overlapping segments to hide the hot turbine interior and to break up radar reflections.
The afterburner section is redesigned to integrate fuel injectors into thick flame holders, reducing the radar signature of internal components.
At full power with afterburner, the engine can produce roughly 43,000 pounds of thrust, pushing the jet to around Mach 1.6.
Air enters through carefully shaped S-ducts that hide the rotating compressor blades from radar, while still feeding the engine efficiently.
The engine sits inside a strong central bay surrounded by frames and bulkheads that carry both thrust and aerodynamic loads.
In normal cruise, the engine runs without afterburner to save fuel, relying on its high bypass core to maintain endurance.
The engine must deliver not only raw power, but also reliable performance for long missions and demanding carrier operations.
Numerous vents and inlets manage heat around the engine bay, keeping sensitive electronics and hydraulic systems within safe limits.
Because there is only one engine, reliability is critical, and the entire aircraft is built around making that single power plant as dependable as possible. When maximum thrust is needed for takeoff, climb, or combat maneuvers, the pilot can ignite the afterburner for a surge of extra power. Behind the engine, the nozzle is shaped not only for performance, but also to reduce infrared signatures that heat-seeking missiles can lock onto.
The combination of thrust and stealth allows the F-35 to sprint when necessary, then disappear again into the sky.
But on the F-35B, the engine is also connected to something unusual, a vertical lift system hidden in the fuselage.
In the short takeoff and vertical landing variant, a large lift fan sits just behind the cockpit, hidden beneath these doors.
A long shaft connects the front of the engine to this fan, and a heavy-duty clutch engages to transfer power forward.
At the same time, the rear nozzle slowly swivels downward, turning what was horizontal thrust into a pillar of vertical lift. Two main columns of force support the jet in the air, one from the lift fan and one from the vectored engine exhaust.
Additional small nozzles at the wings provide fine roll stability, letting the computer keep the aircraft perfectly level.
To the pilot, the controls now feel similar to a helicopter. The computers coordinate
Cold, clean air from above is pulled into the fan and pushed down, which is more efficient and cooler than only using hot exhaust gases.
This vertical lift system allows operations from short decks on amphibious assault ships and from improvised forward bases.
Once the doors are shut and the fan is idle, the aircraft once again presents a clean, low observable outer shape.
This ability to shift from hover to high-speed flight in seconds is what makes the short takeoff and vertical landing variants so flexible.
In engineering terms, it is a balancing act between weight, complexity, stealth, and the vertical lift performance required by the mission.
Advanced flight control computers monitor sensors hundreds of times each second, making tiny adjustments that keep the aircraft rock steady. Unlike earlier jump jets that relied only on hot exhaust, this cooler lift fan stream helps reduce deck damage and hot gas ingestion.
Short takeoff and vertical landing capability comes at a weight and fuel cost, but gives unique basing options to commanders.
After the transition, it behaves just like the other variants, using its stealth, sensors, and weapons to execute the mission. For the viewer, the only obvious clue to the vertical capability is the pattern of doors cut into the fuselage.
To truly appreciate the F-35, we also need to see the hidden electronics and sensors that surround the airframe.
At the core of its awareness is an advanced active electronically scanned array radar that can track air and ground targets at long range.
Instead of mechanically rotating, hundreds of tiny radar elements steer the beam electronically, jumping from target to target in microseconds. Beneath the nose, an electro-optical targeting system combines infrared imaging, a laser designator, and a passive tracking sensor in one smooth fairing.
With this system, the pilot can identify ships, vehicles, and ground targets at great distances without switching on a visible searchlight.
A ring of distributed infrared cameras looks in every direction at once, forming a continuous spherical view around the aircraft.
This distributed aperture system can detect incoming missiles, track other aircraft, and even allow the pilot to see through the floor of the cockpit.
Warning, incoming missile. Locking weapons. Firing sequence initiated.
When the pilot looks toward a threat, symbols appear exactly where that threat is, as if the aircraft were drawing labels on the real world. Behind the scenes, powerful computers fuse radar, infrared, and electronic data into a single picture of the battlefield. The aircraft does not fight alone. It constantly shares information with other fighters, warships, and ground units.
Through secure data links, one jet can silently pass targeting data to another that carries the appropriate weapons.
The helmet-mounted system tracks the pilot's head and eyes so that information remains locked onto the correct spot in space.
In older jets, the pilot had to mentally combine data from separate screens. Here, the fusion engine does that work automatically.
With a combination of touch controls and hands-on throttle and stick switches, the the pilot can command weapons and sensors without looking down for long.
The radar can switch between air search, ground mapping, and electronic attack modes in fractions of a second.
All these sensors overlap, so if one is jammed or blocked, others can still detect and track the threat.
This invisible nervous system is what turns the F-35 from a simple aircraft into a flying information node.
Hidden inside the belly are two main internal weapon bays that preserve stealth while carrying missiles and precision bombs.
These bays can hold beyond visual range air-to-air missiles, allowing the jet to strike without exposing external stores.
Depending on the mission, the Caucasian female pilot can load air-to-air missiles, guided bombs, or a mix of both inside these compartments.
During release, a launcher arm pushes the weapon into the airstream before its motor starts, keeping the bay clear and safe.
Once the doors close, the aircraft returns to its low observable cruise shape, leaving no weapon outlines on the radar picture.
In this configuration, the jet is optimized for penetrating heavily defended airspace to neutralize high-value targets. When stealth is less critical, extra pylons allow the F-35 to carry a much larger load of bombs and missiles.
This heavy configuration trades some low observability for raw firepower, suitable for strikes after enemy air defenses have been degraded.
We'll mix the clean stealth fighters with the heavily loaded bombers.
It gives us the best balance of survivability and payload, Commander.
A stealth-optimized shape can appear on radar as only a tiny fraction of the return from a conventional fighter.
External stores reflect more radar energy, but in low-threat environments this trade allows the jet to deliver more weapons in one sortie.
Wings can carry precision-guided bombs that use satellite navigation and laser guidance for high accuracy.
For air combat, the aircraft can launch long-range missiles without ever coming close enough for the enemy to see it.
The idea is to detect first, fire first, and disengage before the opponent is fully aware of the threat.
After releasing weapons, the pilot can turn away, reduce power, and let stealth and distance keep the jet safe.
Precision allows fewer aircraft and fewer bombs to accomplish objectives that once required large strike packages.
In many missions, the preferred configuration is a small number of careful chosen weapons, kept entirely inside the fuselage.
This mix gives Caucasian male commanders, who are in their 40s, the option to pair stealth scouts with heavy hitters in a single coordinated package.
Regardless of configuration, the weapon system is designed around the idea of striking precisely, while remaining as unseen as possible.
On a mission, a small formation of these fighters can monitor a huge volume of airspace without turning on every active sensor.
The F-35 can also act as a forward sensor for older fighters, passing them targeting data while remaining relatively hidden. In maritime operations, it can search far ahead of a fleet, and relay the positions of hostile ships back to surface units.
Stealth and electronic warfare help it flip between radar beams to locate and disable air defense systems.
These initial suppression missions open corridors for less stealthy aircraft to follow later with larger bomb loads.
There are three main variants of the F-35 family, tailored for Air Force bases, amphibious ships, and large aircraft carriers.
The conventional takeoff version is optimized for land bases, while the carrier version has a larger wing and folding tips for deck storage.
The short takeoff and vertical landing variant trades some internal fuel volume for the lift fan system we saw earlier. Together, these variants allow air forces and navies to share a common cockpit and sensor suite across very different platforms.
The carrier-based design includes stronger landing gear and a tail hook to withstand the shock of catapult launches and arrested recoveries. The short takeoff and vertical landing variant can sprint along a short deck, rotate, and lift off with the help of the lift system.
Different basing options let planners project air power from land airfields, from amphibious assault ships, and from full-sized carriers.
Night operations benefit from the infrared sensors, which can show terrain and targets on the helmet visor even in complete darkness.
To the pilot, cold tanks, vehicles, and buildings stand out in infrared, even when the human eye would see only blackness. Long endurance and aerial refueling support allow the aircraft to stay on station for extended periods, watching and waiting if needed. With tanker support, it can ferry across oceans or orbit over a region for hours, ready to respond quickly. The aerodynamics are tuned for stable handling and a wide flight envelope, rather than extreme agility alone.
The design philosophy favors detecting and engaging opponents from beyond visual range, instead of relying purely on close dogfights.
In this role, its sensors, stealth, and network links are as important as its raw flight performance.
From the pilot's seat, the aircraft is less a single weapon, and more a platform that coordinates many weapons around it.
Supporting such complexity requires careful maintenance and sophisticated diagnostic software running throughout the airframe.
Stealth coatings and composite skins must be repaired precisely to keep radar signatures low from mission to mission.
The sensor reading on the right main gear is spiking intermittently.
Copy that. We'll need to check the harness on the brake assembly.
The trade-offs are real. Unmatched sensors and stealth come with high cost, complex logistics, and demanding training.
Building and sustaining such a system requires deep industrial resources and long-term investment by the nations that operate it.
Pilots train not only to fly the aircraft, but to manage information, prioritize threats, and work as part of a network team.
Even with its focus on systems and stealth, the jet is still capable of aggressive maneuvers when the fight moves in close.
The distinctive wing and tail shape is now a familiar sight in the skies of many allied nations.
Shared training and shared design allow different air forces to operate together more efficiently in coalition operations.
In a future conflict, these connections and this shared picture may matter as much as any single missile fired.
We have seen its stealth shaping, its lift system, its weapons, and its network brain all working together.
The result is a platform designed not for one role, but for many, adaptable as technology and threats change.
From this vantage point, it is easy to forget how much complex engineering hides beneath the smooth gray surface.
Every panel line, every sensor window, every hinge and nozzle has been shaped with a purpose.
In the end, the F-35 Lightning II is more than a fighter. It is a glimpse of how information, stealth, and engineering redefine air power.